Yeah, good morning, everyone. So we can start. We continue with our discussion on elliptic curves. And last time we had looked at embedding degree. And then we want to extend that knowledge now to elliptic curve over extension fields. So what I mean is by extension field, and we had done this when you're looking at polynomials. What I mean is you're given a field, let me say F5, where 5 is the prime number. Now, then you're given an irreducible polynomial, let me say of degree 2. Let me say this is the polynomial of x plus 2. And maybe we are doing this again, mod 5. And I've not checked whether this is irreducible, but supposing it's irreducible, what I mean by an extension of the field is that now you're given this field, you want to extend the elements of this field and make them more. So we'll then have f base 5 raised to 2, where 2 is the degree of this polynomial, the irreducible polynomial. Now, you can come up with any irreducible polynomial, so long as it's an irreducible polynomial. It doesn't need to be this one. Any other irreducible polynomial can be used mod 5. Now, so what we are doing is, for instance, supposing this field has 9 points, we want to increase the number of points. So you can see that this field will have 25 points. That is 5 raised to 2. So we used the field we're given plus this polynomial to add to the elements of the original field. So if the original field had 9 points, our new field, which we now call the extension field, has more than 9 points. They could be 25. Now, if the polynomial was of degree 3, then we are talking of 5 raised to 3. That is approximately 125 points. So that is what we are doing, what we want to do this time. And if you're given a field, you can extend it using an irreducible polynomial to get another field of more points. Now, what is more interesting is that although the original points were the real points we know, like 1, 2, 3, 4. Now, the new field, the extension of the original field, would still have the points of the original field. And then on addition to this, we'll have more other points, and these other points will be in the form of polynomials. So that is what is more interesting, and the only different thing is that now the new field will have other points, and you could have a point like this, 2t, and then 3, for instance. You can see that this point, the x-coordinate here is in the form of a polynomial. You could also have even the y-coordinate being in the form of a polynomial, and so on. So our new points will then be in form of polynomials, because we're using polynomial to extend an irreducible polynomial, using an irreducible polynomial to extend that given field. So that is the only different thing we'll be having this time. And of course, we had looked at this when we were looking at polynomials, because we looked at extension of polynomials. Is the same concept we'll be using here, only that this time we are doing it on an elliptic curve. Now, so therefore, these are the preliminaries. I'm saying elliptic curves of extension fields are very useful in cryptography, in cryptographic applications, and especially our topic, our current topic, which is bearing-based cryptography. So we'll see again how may be used when we go fully into pairing-based cryptography. Now, so this is just what the same thing I've been talking about. So supposing I'm given a field FQ, where Q is the prime number, and then I can extend this field to FQ raised to K, where K will be a degree of the irreducible polynomial that is being used. Because for you to do this, you must have an irreducible polynomial to do it. So the degree of that irreducible polynomial is this power. So that is what, and I had already explained that. Now, again, another point that I've already explained is that the new field that we've just created has extra points in addition to the original field. So if the original field had 9 points, we would still have those 9 points in the new field. But on top of that, we would then come up with other points. And these are the new points I've already said. They'll be represented as polynomials. They'll be represented as polynomials. And the coefficients of those polynomials, the coefficients would be members of the original field. The coefficients. What I mean by coefficient is that if I have x squared, the coefficient is the number before x. The number before x. So if the original field was mod 5, so expecting that we have 0, 1, 2, 3, 4. And so any of these numbers could be a coefficient of x. Any of those numbers could be coefficient of x. That is what you're saying here. That the new points that we've added will be in form of polynomials. And these polynomials will have coefficients, and the coefficients of this polynomial will be members of the original field. So what is more interesting, therefore, is, for instance, supposing I to take an example and see how to come up with the new points. That is what is more interesting. And that's why we want to see what then happens. But remember, we are doing this on an elliptic curve. Now, so supposing the elliptic curve on the original field. So the original field, supposing is that. And supposing the elliptic curve is 1, 1, which means that the elliptic curve is y squared is x cubed plus x plus 1. Supposing this is the elliptic curve we are working on, and it's defined here. Now, when we go to the new field, we retain the elliptic curve. So the elliptic curve remains the same. So the elliptic curve we'll be considering on the new field will be the same elliptic curve we've been considering on the original field. So it does not change. So that is, again, a very important point going forward. So we are not changing our elliptic curve that we're given. It's the one we remain with. The only thing we are doing is that the original elliptic curve that we're given had fewer points, and now we want it to have more points. Want to deal with more points. You know, the advantage of dealing with more points, you want to ensure that your crypto system is secure. So when you have more points, that means security is more, because nobody is able to use guesswork to find out which point you used in your encryption or in your decryption. So that is why we are doing this. You're given a field that has fewer points. You want to deal with more points that can really confuse. And of course, when you are dealing with points that are in form of polynomial, again, you're enhancing the security. That is enhancing the security. Because dealing with the polynomials now again becomes more complicated for people or hackers. Now, so a point I'm just emphasizing this, that we had the original field here, had the fewer points, And now we have a new field on the same elliptic curve, we retain our elliptic curve. Elliptic curve was E, it's in both cases. But now this new field is larger and have different properties. Just say, of course, the points would be in form of polynomials. We are expecting different properties from the original properties. Now, I think it's now good we go to an example just to see, because all these points I've already explained. But the only point I need to again emphasize is this. As we go to now creating points, how do we normally create points? Just use let me use the original field. I'm using the original field. How do we normally get points on the elliptic curve? So once we know that, then we can be able to also understand how we'll be coming up with a code that will assist us. Because now when we are dealing with more points, when you deal with more points, it will not be easy for us to do it manually. The only easier way to do it is by use of a code that can give us those points. Now, supposing our elliptic curve is this. How do we get points on this elliptic curve? This is how we normally do it. Yes, and we are doing it mod 5. We are doing it mod 5. So x can be n of those values, mod 5. So we just want to find the value of y. Before that, you get y square, then you get y, because y will be the square root of y square. Y square is what is on the left-hand side. So you then try 0. If x is 0, you find that y square will be 1. What about y? Y will be the square root of 1, which is plus or negative 1. So that means when x is 0, y can be 1. That is the square root of that. Another thing is that when x is 0, y can also be negative 1, but we are talking of negative 1 mod 5, which is 4. So that means, what point have we obtained? When x is 0, y can be 1, that is a point. Another point is that when x is 0, y can be 4. So those are already 2 points. That's how we get points on elliptic curve. Manually, this is how we get points. Now, what about when x is 1? Again, you try. When x is 1, you'll be having 1 square plus 1, then plus 1. 1 plus 1 plus 1. That is 3. So y square is 3. Then you want to ask yourself, what will be the square root of 3 mod 5? What will be the square root of 3 mod 5? So you just try. You're doing it mod 5. You try. You want to see whether 1 is the square root of 3. You find that it's not. 1 is on the square root of 3. What about 2? 2 is 4. It's not giving us 3. So 2 is not the square root of 3, therefore. What about 3 itself? This would be 4. Because it's giving us 9. And you're doing it mod 5. It's giving us 9 and you're doing it mod 5. So that doesn't give us 3. What about 4? Mod 5, this is 1. Okay. What about, we've exhausted 1, 2, 3. So that means when x is 1, there is no point. There'll be no value of y. There'll be no value of y. That's what you're saying, because we did not get the square root of 3. 3 has no square root. 3 has no square root. Okay. Now let's see, can we get a point when x is 2? When x is 2, again, we just go back to the equation of the elliptic curve. Want to find what is y square. What is y square? So we have 2. 2 cubed would be 8 plus 2, then plus 1. This is 10. This is 10, 11. We are doing mod 5. So that means y square is 1. Because we are doing mod 5. So again, it means we had already found the square root of 1 as 1 and 4. So the other point that we have is that when x is 2, y can be 1. And when x is 2, y can be 4. That is another point. So again, you try 3, you find the other point. So this curve will have 9 points. The other point is the point at infinity. Then you try when x is 3, and so on. When x is 3, what you have is 3 cubed plus 3 plus 1. Okay, 3 cubed is 27. Is it? Yes. 3 times 3 times 27. Then 27 plus this will be 30. Then again 1. Then again this will be 1, 4. This is just a coincidence that this time we are getting the same value of y, but it's not always the case. So we have 7 points now. We try 4. Because there are supposed to be 9 points. This curve has 9 points. 4 cubed. This will be 4 times 4 times 4. But you notice that this is 1. 4 times 4 is 1. Then times 4, which is 4. Then plus 4x. No. This is 1, 4. But the x is 4. So what we have is plus 4. Then plus 1. This is 8, 9, which is 4. So y square is 4. The square root will be 2 and negative 2. Negative 2 is 3. So you have another point that is 4, 2, and 4, 3. So how many points do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, 9. Now, that is one way you can find points on the elliptic curve. That is one way. That is one way, but it's not the way I'm going to use for this kind. For this kind, the other way that we find points on the elliptic curve, let me just again show you, is what we call cross product. Because what we understand is this, that if you are given this elliptic curve, we understand that the values of x will be, and we are doing it mod 5. We understand that the values of x should be 0, 1, 2, 3, 4, 5. No, just 4. What's the values of x? And the values of y, you understand that it should be 0, 1, 2, 3, 4. That is values of y will also be in that range. You cannot have value of y that is more than 5. So then we want to find a coordinate xy. To find a coordinate xy, just combine that. You can have 0, 0. So 0, 0 will be the point at infinity. That would be the point at infinity. And then you can also have 0, 1. You can have 0, 1. Then what I'm writing here just possibilities, but then you have now to verify which one is true. So I'm just giving possibilities of points we can have. Possibility of points we can have. So we can also have 1, 2, 0, 2. You can have 0, 3. You can have 0, 4. You're done with the 0. You can have 1, 0. So 1 with that. 1, 0. You can have 1, 1. And so on. So how many possibilities do we have? 1, 2, 3, 4, 5. So you see the first one, 1, 2, 3, 4, 5. 5 times 5 will be 25. 25 values to check. So you just check. You want to check whether which one satisfies the equation. The equation is y square is x cubed plus x plus 1. So you want to check if they satisfy the equation. For example, if you put x to be 0, y can never be 0. But now this one, we just call it a point at infinity. So we don't have 0, 0. Because when x is 0, y can never be 0. Now you try this 0. When x is 0, you can see that y square will be 1. So it means that y can be 1. So this point is true. When x is 0, you try now this. When x is 0, we found that when x is 0, we found that y is supposed to be 1 or negative 1, because that is the square root of 1. The square root of 1 would be 1 or negative 1. But negative 1 mod 5, that is 4. That means this point is correct. Now, which one am I trying? I'm supposed to be testing these ones. That way. Okay, so we've already found that this point is correct. So that is why it's there. Now, when x is 0, y can never be 2. Because when x is 0, we found that y can be 1 or 4. So y can never be 2. So this is not a correct point. But we were saying that these are possible points. So after you found the possible points, you now find out which ones are the real points. Of these possible points, which ones are the real points. So when x is 0, again, y can never be 3. When x is 0, y can be 4. So this is correct. Now you check when x is 1. When x is 1, we have 1 cubed plus 1, which is 2 plus 1, that is 3. So y squared will be 3. But we found that there's no square root of 3 mod 5. That means when x is 1, there can never be a point. There can never be a point, and so on. So that's a method I'll be using for this extension. This extension, that is. So how many points have we tested? We were to test 25 points. Because we took 0, 0, 0, 1, 2, 3, 4, 5, then crossed it by 0, 1, 2, 3, 4. And we were to get 25 points and test each of them. So that is why I was saying, then if we have F5, we have 25 possible points to test. These ones are few, we can test all of them. But if you have F5 raised to 2, this is the same as F25. So that means you have 25 times 25 points to test, which is 625. And those are so many points. You cannot test all of them. So that is why I said for this case, it will be possible for us, it will be easier for us to use the code instead of testing all the points. Now, so we just add a smaller field, F5, and when we use a polynomial, you can see that you now have very many points to test. So that is the one advantage of doing this field extension, that when you have a smaller field, and of course, normally they work with the smaller fields, but now you want to increase the number of points to work with. So instead of using 9 points, you now increase them to more points. Now let's look at this example. Consider this field F5, and the elliptic curve is this, or the one I've been explaining. Construct the extension F5 raised to 2, which we can easily write as F25. And I've wanted to use this polynomial. Of course, you can use another polynomial that is reducible here. But not necessarily. You see this power. This power is the embedding degree we talked about. The embedding degree. So when you get to the embedding degree, it becomes easier for you to know the power of the polynomial that you are going to use. It becomes easier. And how did I come up with this power? How did I come up with this power? This power, after discovering that this one has 9 points, I ask myself, what is the divisor of this? And the divisor of this is 3. Then I find the embedding degree. So the embedding degree is the smaller k, such that 3 divides this equation, this part. But what is q? Q is 5. Q is 5. So 5 raised to k minus 1. So what is this k so that 3 can divide this? So then I find that this k is supposed to be 2. Because if I have 5 raised to 2, then minus 1, this will be 24. And 24 can be divided by 3. So that's how then I settle on that 2. So that the polynomial that I'll be using has power 2. That's how I settle on that. So it's easier to use power 2 in this case, instead of using power 3 or trying to think of what polynomial will be irreducible here. It's easier, you get the embedding degree. Once you get the embedding degree, you can know the power of the polynomial. Then now this other part, you can just try to play with it and see which one gives you an irreducible polynomial, this other part. But for the power you can always determine using the embedding degree. Now, so the question is, you have this polynomial, this field, and this is the elliptic curve. And the question is, can you find the points? When you say construct an extension, it's just telling us, find the points of this new field. Find the points of this. Of course, is the elliptic curve. The points of this elliptic curve, find the points of this elliptic curve on the new field. That's what the question is telling us. Construct the extension field f base of 5 raised to 2, which we can easily write as that. Now, so you can see that we want to find the points x, y. But we already know that this will be the same as x is 0, 1, 2, and they are going all over up to 24. And y is supposed to be 0, 1, 2, 3, and again all up to 24. So how many points are we expecting? We're expecting, if we do this, and then that, we have 0, 0, we have 0, 1, we have 0, 2, all the way up to 0, 24. And this will be 24 points. This will be 25 points to try. And then if you have one that, having 1, 0, 1, 1, 1, 2, all the way up to 124. Then after that, you have 2, 0, 2, 1, 2, 2, all the way up to 224. So in total, you'll have 25 times 25, which is 625 points to try. So you see, you'll be trying. You want to try whether when x is 0, y will be 0. So you try that equation, and you're doing it mod 25 this time around. You're doing it mod 25. So you're trying if x is 0 and y is 0. Now, if x is 0, can y be 0? Mod 25. What about when x is 0? Can y be 1? When x is 0, can y be 2? And then you do the 0 part up to this point. And then you try again. When x is 1, can y be 0? When x is 1, can y be 1? When x is 1, can y be 2? So you have so many points to try. And so to avoid doing all this, we come up with a code that will assist us, will check for us all the 624 points, and then give us the points of this elliptic curve. To give us the points on this elliptic curve without so much struggle. So when I employed my code, my code was able to give me these points. My code was able to give me these points. That this new and this elliptic curve on the new field has these points. This is a point at infinity, then 0, 4, then that, then that. I think these are how many points? That are they 27 points? These are 27 points. I think they're 27. Let's just count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first 9 points are the points on the original curve. On the original, on the elliptic curve under the original field F5. Under the original field F5. Then these are now the new points that we've added. The first point is that, the second point is that, and that, and that. And I say that these new points will be in form of polynomials. And you can see they're all in form of polynomials. These are the new points. Now, if you check, you find that they are, of course, on the elliptic curve. Just want to show you that these points are on the elliptic curve before I show you the code that generated them. Now let's see that. Let's show that they're on the elliptic curve. Our elliptic curve is y squared is x cubed plus x plus 1. And our new mode is now 25. Of course, it's easy to show that these other points are on the elliptic curve. This one is easy. So the ones I want to show are the ones in the polynomial form. And for this one, it's very easy. For instance, when x is 0, you can show that y will be 4. Let's see. When x is 0, you would have y will be 1. So the square root of y square will be 1. What about y? Will be the square root of that. And we are doing it mod. So this will be 1 or -1. It's supposed to be mod. We just do it mod 5. Just do it mod 5, not the new mod. Okay, this one is just guiding us. We're just extending. And now in our calculations, we use 5. In our calculation, we use 5. We've done the original elliptic curve, but we just extended. We've added new points on that. So this will be the same as 1 and 4. So you can see that when x is 0, y is 1 and y is 4. So you can also try when x is 3 and see that 4 will be a result. Y will be 4. But now I'm interested with the ones in polynomial form. How do we show that they are on this elliptic curve, mod 5? So we've enabled this elliptic curve mod 5 now to have more points than originally had. It had 9, and now we've added more points. Now I want to try and see that this is on the elliptic curve. So we try where there is x, we put the x value. So this would be the same as 40 plus 3, that is the x value, cube. Then plus okay, so then plus x is 40 plus 3, then plus 1. We want to see whether the y value will be this. This is what we want to see. We want to see whether that will be the y value. So we just cube this, we cube this one first. So 40 plus 3, or first of all, we square it. 40 plus 3. When you square this, and of course, then we shall multiply it. We shall multiply 40 plus 3. This is how we cube it. Let's keep this one pending first. Keep this one pending. Now let's do the first two. That will be 16t square. 16t square. And that will be 12t. That will be 12t. Okay. And again, we shall have another 12t. And then we have a 9. So what is this? When you just simplify this, you have 16t square, then plus 24t. But remember, we are doing it mod 5, then plus 9. So when you remember that we are doing it mod 5, it means that this will be t square, because we are doing it mod 5. And this is 24, so it's 40, and this will be 4. Okay. So this is when we square. But we're supposed to cube. So again, we multiply it by this other one. Just assuming that my calculation there is correct. And what we are doing is we are trying to show that the new point we got, of course, is on the elliptic curve. That's what we want to show. So we're supposed to multiply it by this one now. 40 plus 3 multiplied by t square plus 40 plus 4. Now, when you do this, but this t square can even do away with it. You can do away with it because our original curve was, the polynomial was, what was the polynomial? Let me just look at the polynomial. Oh, it was t square. The polynomial was t square plus 2. So when you equate this to 0, it means that t square will be negative 2. T square will be negative 2. So where there's t square, you can always put negative 2. That is the easiest way of doing this. Where there's t square, you can always put negative 2. So that we reduce our polynomial, we don't work with this. So this one will be negative 2. Because it's t squared, it will be negative 2. And so this will be 40 plus 3 multiplied by 40 plus 2, which then gives you 16 t squared. But remember, t squared will be negative 2, which you just write negative 2 later on. And this will be 8t, 8t, and this will be 12t, 12t, and this other one will be 6. And remember, you're doing it mod 5. You're doing it mod 5. So I'm just hoping that the calculation we've done is just correct. That's why I'm erasing it. Now, so this is 16t squared. The 16 mod 5 is 1. So in fact, we're talking of t squared. 8t plus 12t is 20t. Mod 5, that is 0. 20t mod 5, that is 0. Then 6 mod 5, that is 1. So then what we have is t squared, which you said is negative 2. Then plus 1, which is negative 1. So cubing this part has given us negative 1. Okay, let me just erase this one. You see what you're talking about. So what I'm just saying is that this part has given us negative 1. This part, 4t plus 3 cubed has given us negative 1. Now add 4t to it, then add 3. Of course, 3 plus 1 is 4. So when you do this, you would find that you have 4t plus 3. 4t plus 3. 4t plus 3. So this is a y square. What about the square root of that? So our y square, we've now found it to be, let me write it at 3 plus 40. That's a y square. Now, so what we wanted to show, that this point was on the curve. So I wanted to show that when x part is this, then the y part will be this. So what I want now to prove is whether this is a square of this. I just square it. So why I've seen that y in this case, y that we have is 3t plus 4. So I want to square it and see whether it gives me y square. So y times y, therefore, is 3t plus 4 times 3t plus 4. When you do this, you have 9t squared. And then this would be 12t, 24t, then plus 16. So I just want to square it and see whether I get y squared that I have there. I want to see whether I get that. Now, of course, 4t, 4, no, 9, 9 is 4. This is 4t squared, but t squared is negative 2. T squared is negative 2. This is 24, mod 5. This is 40. Mod 5, this will be 40. And then 16, mod 5 will be 1. My pen is not writing properly here. Okay. Let me write it somewhere else. It is 4 into negative 2. Negative 2 is the t square. Then this other one is 24, which is the same as 4, 40. And this other one is 16, which is the same as 1. You're doing it mod 5. So the first bracket here is negative 8. Negative 8. And then plus 1, that would be negative 7. Plus this one, negative 7. Then plus 40. We are doing it mod 5. So that means we make it positive. We add 5 to it until we get a positive number. So this will be negative 7 plus 5 plus 5, then plus 40. So this will be the same as this. 3 plus 40. So you can see we proved that this point, of course, is on the curve. And you can prove all the other points that they are on this curve. On the curve, on the elliptic curve that we're given. Mod 5. Mod 5. So this polynomial has assisted us to get more other points on the same elliptic curve. Without this polynomial, without this extension, we would only have gotten 9 points. Then we would not have known that this elliptic curve has even more points. We would not have known that. But field extension now teaches us that the elliptic curve can have as many points as possible. So you don't need to worry that you've chosen an elliptic curve that has fewer points. By the knowledge of extension of fields, you can discover that the elliptic curve that you have has so many points. Some are polynomials. That is why the knowledge of polynomials is very important before doing elliptic curves. Now, so then let me now show you my code. My code, so that you learn how to use your code. You have my elliptic curve. You can always extend so that your elliptic curve has as many points as possible by using the knowledge of field extension. Okay, so my main function is here. But where I input my values is here. My f value, you see, I'm dealing with the polynomials this time. So this value 0 here is very important because it means that the polynomial value for t here is 0. It must be there. Now, so my elliptic curve was 1a, no, a was 1 and b was 1. I want to extend it over a polynomial f2. So I define it here. I've defined, I want f, my field is 5. My mod is 5, but I want 5 raised to 2. I want 5 raised to 2. So I begin by defining those as I I move along. I'll show you how it works. I'm just showing you how it, what I wrote. Okay, let me now find how many points are here. Which points? Supposed to give me the points, of course. Now you can change where there's 5 and use another mode, and you can change 2 to be another power. But remember, the power must be the embedding degree. So you can always so when I do that, when I run it, gives me the points on the elliptic curve. And before that, it tells me that the elements on this could be 0, could be 1t, could be 2t, 3t, 4t, 1, and so on. So these are the elements we are trying to multiply. Remember, I had said that if you have mod 5, you'd have 0, 1, 2, 3, 4 crossed by 0, 1, 2, 3, 4 to give you 25 points. Now, but if you have mod 25, then you have these 25 points. These 25 elements, 0, 1t, 2t, and so on, which you will then be crossing. And when you cross them and then cross-check which ones satisfy the equation, you will find that the following satisfy the equation. So these are the points on the elliptic curve, on the extended elliptic curve. These are the points. There are 25 of them. There are 25 points here. No, 27, I think 27. Now, so this is where you begin. The function, the main function. Now, let the field of elements. So you're just calling on the field of elements. This is a function above and is mutable. This is a function above. You're just calling on it. Now, so what we'll be doing here, we'll be storing the elements here in vector form. They'll be stored here. And we are doing it, A has values from 0 to 5, because we are doing it mod 5. And B also has values from 0 to 5. So from 0 to 5, can you come up with the field elements? And once you come up with the field elements, push them here inside this vector. Push them inside that vector. So just going through 0 to 5. For A, 0 to 5. And for B, 0 to 5. Come up with the elements that would fulfill the equation of the elliptic curve, and then push them here inside this vector. Then print all the elements of this extended field. Print all of them. So this main function, of course, just calling on other function that is then assisting it to perform these roles. Let's begin from above. Now here we just we are defining the elements of the elliptic, of the extended field. We are defining the elements of the extended field, how they should look like. And then there is the implement. Okay, now this is more important, this part. Let me show you what it means. Now, if we get a point 0, 0, a 0.00 will be written as 0. Now 0 here is the x value and this is the y value. The y value is always expected to be polynomial. But the x value here is expected mostly to be the value from the field. It's coming from the field mod 5. So it's an element of mod 5. So it could be 0, could be 1, could be 2, could be 3, could be 4. That is why you can see here. That's why you can see. Let me just show you. When you look at these points, this is the x value, an element of mod 5. This is another one, mod 5. This one, another one, mod 5. So the x values, all of them are mod 5 elements. The x values, all of them are mod 5 elements. Now, but now you can even add to it. You can, but this is the first value. This value is mod 5. This value is mod 5. So you can add to it an element to it. Now the polynomial, you can add a polynomial to it. You can add a polynomial to it and so on. Now look at this one. This is, so when you have a0, what you write is just a. That is what will be displayed, will be just be a. When I have 0b, what will be displayed will be this. Will be 0, then b. So I understand when you see that, you understand that 0 is coming from mod 5. And b, this b must have a t to be displayed. This one will be displayed. So what will be displayed will be 0 plus bt. But 0 here is irrelevant. 0 there is irrelevant. So bt is what will be displayed. What about this? So this one, what is supposed to be displayed will be supposed to be a plus bt plus bt, a plus bt. That is what will be displayed. Okay. Now, how would we add the two elements? We just add the elements the same way we add on the elliptic curve. Every time we do that, we reduce it to mod 5, we reduce it to mod 5. So if you're adding a to itself, the answer should be reduced to mod 5. If you are adding b to itself, the answer should be reduced to mod 5 and so on. And again, when you're multiplying, supposing you're multiplying a times a, we expect that the answer will be either negative or positive. That's why we are doing it I16. But you can do it I anything. You can do it I32, I, and so on. But I here means you, and at this level, you are dealing with both. You could be dealing with the positive or negative values at this point. Then polynomial, how do you multiply polynomials? If I was to multiply a times c, the answer that I get should be reduced to mod 5. If I was to multiply b times d, the answer that I get should be reduced, and so on. So if I was to multiply a times d, then plus b times c, the final answer should be reduced. So you're just telling the code to do that. So whenever the code does multiply, it reduces those values, mod 5. Now, so you also have to define the polynomial that you're working with for your code. So you must tell the code, this is a polynomial I'm working with. Now, so what the polynomial will be doing, just the same way we did. So whenever there is t square, whenever t square appears, this code is supposed to replace it by -2. So just equate, it will equate this polynomial to 0 and then make t squared the subject of the formula. So wherever there will be t squared appearing in the computations, it will understand that t squared is -2. Then it will replace that once you've given it to the polynomial. And this is what, or that's what I've done it to you. You're not seeing that. This is -2. I was forgetting to explain that. So supposing that this is -2. 3. -2 mod 5 is 3. So this is -2. So I've already told it what to do there. So you are not expecting to see polynomial, but the polynomial is already put in my equations. +3 is -2. Okay, of course I've added the notes on how the polynomial that node working. So you'll be looking at the notes on how the code works. But you've seen that the code has given us all these points on the elliptic curve, and of course I've shown you by this example that this point is on the elliptic curve. Which elliptic curve are we referring to? We are referring to the elliptic curve y is x cubed plus x plus 1. Under mod 5, this elliptic curve had only 9 points. But now under field extension is the same elliptic curve, but this time it has 27 points. And all these are the points. So you can see that you can be working with the same elliptic curve, a very small elliptic curve. You don't need to come up with a very big, very complicated elliptic curve. Just come up with the same small elliptic curve, the one you can handle, and now define a field extension. And the field extension will enhance it to have several points. And you can always use these points for cryptographic protocols and so on. And your system will be secure. Of course, now you'll be introducing points that are polynomial and so on. Now, so let's look at how to add these points, because that is what is very important now. You have these points on the elliptic curve. Can you add them? Can you double them? Can you multiply them with the scalars? That is what is important, and that's what happens here. That's what happens in elliptic curve. We must know how to add points on the elliptic curve. Remember, and again, let me remind you, although we are dealing with this, but your manipulations, your addition, your scalar multiplication, remember the original mode. The original mode was 5. So everything you are doing, whether addition, multiplication, and so on, you're doing it mode 5. You're doing it mode 5. So I want to see whether you can add these points. Now you'll go through the code, and then you go through the notes. I've added the notes for how it works. These are the notes on how it works. I've explained every function, whatever function will be doing. Now, so I'm looking at the same, this is an example. And this example, I'm looking at the same curve where a and b are 1, x cubed plus x plus 1. And you're still using the same polynomial. Now I want to see whether I can add p plus q. and P is this, and this. These points are on the curve. These points are already on the curve. Can I add them? Can I add them? So adding points, we use the same formulas we talked about. Only that this time we remember we are doing it mod 5 and there's a polynomial to assist us. If points are polynomials, in this case, these points are not polynomials, so it will be easy to do it. But I'll now look what if they were polynomials. This is my point P. I don't need to check whether it's on the elliptic curve because that is already, it's obvious, it's been the elliptic curve. But if I did it, I verified here that it's on the elliptic curve, just for purposes of making it complete, so that you know how to verify if a point is on the elliptic curve. But it's not necessary because we already, it's that elliptic curve that gave us these points. And now to verify if 2, 4 is on the elliptic curve, we just substitute 2 here on the elliptic curve. The elliptic curve is y square is x cubed plus x plus 1. So just put 2 where there is x. You'll be getting y square when you put 2. So this will be 8 plus 2 plus 1. We are doing it mod 5. This is 1. So y square is 1. So what about when y, can y be 4 when x is 1? Just square 4. Just square 4 and see whether it gives you y square. So y in our question is 4. What about y square? Is 16, and again that is 1. So it's shown that when x is 2, y square will be that. And when we try to square the y that was given to us, it has given us the same y square. So it means it's true that this point is on the curve. It's true. The point is on the curve. So you see, if you don't know if the point on the curve, is always good to verify. If you don't know if it's on the curve, it's always good to verify. That is not what we want to do. What we want to do is to add the 2 points given to us. So here I was come. Now, so how do we add the points? The points, for you to add them, first of all, you check if they're on the same vertical line. Because if they're on the same vertical line, it's easier that their sum will be a point at infinity. We've been given 2, 4, and 3, 4. They're not on the same vertical line. We've given 2, 4, and 3, 4. They're on the same vertical line. They're not. If this is the y-axis and this is the x-axis, 1, 2, 3. So x is, the first point is somewhere like here, and the other one is 2, 4, 2, 4. Somewhere like here, and the other one is somewhere like here. So they are on a horizontal line. They are not on the same vertical line. If they have been on the same vertical line, the answer will have been point at infinity. That would be the sum. Now, since they are not on the same vertical line, we also need to find out whether it's the same point. Because if it is the same point, the formula will be different. And we can see that these are 2 different points. These are 2 different points. So since that there are 2 different points, this is how we find the gradient. Change in y over change in x. So change in y will be 4 minus 4 will be 0. And change in x will be 3 minus 2 will be 1. So the gradient is 0. Now, once you find the gradient, you need to find the value of x3. For the new point, x3 is given by this formula. Gradient is square minus x1 minus x2. And y3 is also given by this formula. Gradient into x1 minus x3, then minus y1. So this is the formula. Now, but the gradient is 0. X1 is that from the question. X1 is 2 from the question, because we're talking about this point. X1 is 2 and X2 is 3. X2 is 3 and Y1 is 4. So just substitute why there is X3, substitute these values and find what the new coordinate of the sum is. Because when you sum them, it gives you another point. And so it's that other point that we're looking for. It's X coordinate and it's Y coordinate. So X3, when you substitute these values into this formula, you have 0 square minus 2 minus 3. This is minus 5. You're doing it mod 5. The remainder will be 0. So X3 is 0. When you substitute these values here to get Y3, you have 0 into 2 minus 0 minus that. This first bracket gives you 0. So you have negative 4. You add 5 to it, get 1. So the new point of the sum is this. That is the new point of the sum. Okay. Now, so I had a code for summing up. So you just sum up. There's a code I wrote for summing up. So we are summing 2, 4, 3, 4. Let me share that code. This is the code for summing up. It's just the same code like the previous one, just changed a few things so that it can do computation, it can sum up. So it's just the same code like the one above, just a few changes. Now I'm still using A1 and B1. I want to sum up 0.24 so it is 0.24. So the t value, the coefficient is 0, and this is 0. So you know what I've written here is this. 24, this point, since I'm dealing with a polynomial, I'm just typing here to see what I want you to see what why I've entered that. So I've taken this point to be the same as the x coordinate to be 2 plus 0t, and the y value to be 4 plus 0t. So that's why you can see here I've written 2, then 0t here. Then this one is 4 plus 0t. So because the point is supposed to be in form of a polynomial, it's supposed to be in form of a polynomial. So the x value is supposed to be form of a polynomial, and the y value is supposed to be form of a polynomial, where the first element here is coming from mod 5. It's one of the values mod 5. And this one is also one of the values mod 5. And the coefficients are also mod 5. Now for this other one, it was 3, 4. 3, 4. So again, it would be 3, 0, and then 4, 0. So when I now ask for the sum, ask for their sum, Yeah, you can see what it has printed. You can see what it has printed down here. It has said P1 that was entered was 24, and P2 that was entered was 34, and that their sum would be 0, 1. Their sum would be 0, 1, and I think that is what you are getting. Their sum would be 0, 1. So you can see it's very good to know how to enter the values here. You understand what? Because they are supposed to be in the form of a polynomial. Every time you are doing that, you must remember that. That the sum is 0, 1. When you look at our computation, yes, our computation, the sum was 0, 1. That was our okay. So that is where I want to. That's what I wanted us to look at today. But then when we meet next time, we shall continue looking at these computations on the same. We look at how do we add the points, especially if points are polynomial, so that we look at them. It's good we stop there so that you can remember what we talked about. And then when we meet, we now look at more computations. How do we add if they were polynomials? And how do we multiply them with the scalars? So I think that is what we'll be looking at maybe on Thursday, no, on Tuesday. Yes, that's what we'll be looking at. Is it Tuesday or is it's tomorrow? Yeah, it's tomorrow. It's tomorrow. Tomorrow at night. Because today is Thursday. So that's what we'll be looking at, so that we know how to. If you're given us an elliptic curve, how do you then come up with several points that we can work with to ensure that you are working with a very secure thing? The more points you have, the more secure your crypto system is. Okay, thank you.